Hey everyone, today we're talking about section 5.2, that's logarithmic functions. This is the last lecture of the year, hooray, and this is our last function family that we'll deal with here. Logarithmic functions are highly related to exponential functions. In fact, we can see that in the definition. So definition, a logarithmic function with base b greater than 0 and b not equal to 1 is of the form y equals log base b of x. So y equals log base b of x. This is the logarithmic function of with base b. Okay, and this is true if and only if x equals b to the y. Okay. So the logarithmic function and the exponential function are related, and you can see here that we have kind of flip-flopped our x and y values in our exponential from our logarithm here. So what this is saying, so note, remember when we switch the x's and y's in a function, we are dealing with inverse functions. So exponentials and logs are inverse functions of each other. So we know exponential and log functions of the same base are inverses. Okay. So basically, if we are given a log, we can represent it as an exponential, and if we're given an exponential, we can express it as a log, okay, by doing a little bit of rewriting, okay? So we want to express the exponential in log form, okay? So let's start out with a simple one. How about 9 equals 3 squared. That's true, right? So let's say we have this exponential form, or 3 squared equals 9, same thing. So here, let's identify some values here. So here we have 3 is our base, right? 2 is our exponent. And 9 is, let's say, our answer. Okay? So if we want to switch this into exponential, from exponential form to logarithmic form, we just kind of use this procedure here. So this implies, this is of the form x equals b to the y, right? So our log form, just follow this little pattern right here. So we can write this exponential in logarithmic form as, well, what's our y? Our y is the exponent here, so that would be 2. Is equal to log of the base. The base is 3. And our answer is 9. Okay. X is our answer. X goes there. So you can see that these two things are equivalent in nature here. So notice something with the log expression. So the outcome of a log is always an exponent, right? It's always an exponent. So basically, if we were to see just this expression, we try to evaluate this log, we ask ourselves, what power do I raise 3 to so that the outcome is 9? And the answer would be 2, right? Let's rewrite another one. So how about 8 to the 1/3 equals 2? So here's our exponential form. If we go to logarithmic form, we would have log of, what's the base? Well, the base is 8. Now the big number is always the answer, so that would be 2. And logs are always equal to the exponent, so this would be 1/3. So log base 8 of 2 is equal to 1/3. We can also go in the flip, in the opposite direction. So we're going to express log as an exponential. Let's say log base 3 of 27, well, let's say 81 equals 4. So here's our logarithmic form. To go to the exponential form, look for your base first. What's your base? Is 3. Now what's the power here? So recall that the answer to a log, the outcome of a log, is the power, right? Outcome of a log is the power. So this would be 3 to the 4th equals 81. And that's absolutely true. If you multiply 3 times 3 times 3 times 3, you'll get 81. Okay. And last up, let's do log base 10 of 0.001 equals -3. This transfers to exponential form as we'll locate the base, that's 10. The exponent is just the other side of the log, equals 0.001. Well, this is absolutely true, right? Because what's 10 raised to the -3? 10 raised to the -3 is like 1 over 10 to the 3rd power, or 10 to the 3rd power is 1,000. And if you were to plug that in your calculator, you get exactly 0.001. So this is how logs and exponentials are related. They're inverse functions of one another, so we can always express one as the other. Okay. Let's do some evaluations. So how do we evaluate log expressions? Example, evaluate how about log base 4 of 64. So we want to see what this is equivalent to, right? See what this is equivalent to. So how do we do that? Well, it's easiest to use exponentials, right? Because we're more familiar with exponentials, it's a good idea to rewrite this in its exponential form. So what I'm going to do is set this equal to x, let's say. And set it equal to x. This is our unknown. We're trying to figure out what this is equal to. Now let's switch it to exponential form. So equivalently, this would be 4 to the x equals 64. Okay. Now all we need to do is figure out what that power of x should be so that when we raise 4 to it, we get 64. Well, 4 times 4 is 16. 16 times 4 is 64, right? So x is equal to 3, right? At 4 to the 3rd power is equal to 64. Therefore, x equals 3. Okay? Or, equivalently, log base 4 of 64 equals 3. Let's try another one. How about log base 9 of 1/3? Okay. So that's equal to our x, yes? So that means we're looking for 9 to what power? Equivalently, this means 9 to what power gives us 1/3? Okay. So this one's a little tougher, right? So in order to get us up to 1/3, what we need is x can't be a whole number, right? Because 9 to the first power is already 9. 9 to the second power is 81. 9 to the 0 is 1. So we need some negative power here, right? We need a negative power to get us there, okay? So let's think about it. How can we do this? Well, we know that the right-hand side can be written as 3 to the negative 1 power, right? Now the left-hand side is 9 to the x, which we can actually rewrite, right? 9 is actually 3 squared, isn't it? We can get the same base. It might be helpful. This is like 3 squared to the x. That's true. Now here, notice 3 to the 2 to the x is 3 to the 2 times x, or 3 to the 2x. So we're looking to see for what value of x, 3 to the 2x is equal to 3 to the negative 1. Well, this implies that we are looking for the solution to this equation, which is negative 1/2. So once we get it to exponential form, we can try to equate our bases to make sure that we can equate those exponents, right? We could actually do that for this problem up here. Instead of guessing the value of x, we can try to express 64 as a power of 4. Let's do one more. How about the log base 6 of 1? So log base 6 of 1. Let's rewrite this in exponential form. That would be 6, say, equals x. 6 to the x equals 1. Okay. Well, let's think about this. We know that when we raise anything to what power gives us 1? 0, right? So that is x equal to 0 there. Or log base 6 of 1 equals 0. All right, now that we know the connection between exponentials and logs, we can try to graph some of these things. All right, so graphs of log functions. So let's start out with an example. So we want to graph log base y equals log base 2 of x, let's say. Okay. So here we have a function, x varies, and then y will vary as well. So instead of actually evaluating this log explicitly at different values, what we can do is use that fact that these guys are inverses of one another, right? So what we're going to do is first graph the exponential function, right? Because if we were to re-express this, this would be 2 to the y equals x. Right? Let's make a table of values of this function, and then we'll just flip-flop the values like we did when we used inverses, okay? So let's say x and y equals 2 to the x. And let's put our basic values in. Let's do -2, -1, 0, 1, and 2. Okay? Right, so let's evaluate here. So 2 to the second power is 4. 2 to the first is 2. 2 to the 0 is 1. 2 to the -1 is 1/2, so 1/2. And 2 to the -2 is 1/2 squared, so that would be 1/4. Right? Now, utilizing inverses, we can get the values for our log function. So all we're going to do is flip-flop our x's and y's to make our logarithmic graph. So for our x, y equals log base 2 of x, all we need to do is flip-flop this column for that column. So 1/4, 1/2, 1, 2, 4, -2, -1, 0, 1, 2. Okay. So that's it. It's easier to make the exponential and then just flip-flop the values there. Okay? So let's graph those points. All right, so looks like our x's are all positives. So let's say 1, 2, 3, 4. And then our y's are both positive and negative. So -1, -2, 1, 2. Okay. So let's plot some easy ones first. So 4, 2, we have a point 4, 2. It's right there. 2, 1. 2, 1. And 1, 0. 1/2, which would be about here, -1. And 1/4, -2. So you can see here, our log curve looks something like this. So it just increases in this direction. Now notice that I've drawn it so that it's kind of not crossing the y-axis. And this is the case because, note that our x's cannot take on a value of 0 because our y's from the exponential cannot take on a value of 0. Remember we said that the domain of this function was -infinity to infinity, but the range of this guy is 0 to infinity. Therefore, our domain and range will flip-flop here. So here, the range from here was 0 to infinity, and our domain was all reals. So recall when we flip-flop those x's and y's, the domain of our logarithmic function is now the range of the exponential, and the range is all reals. So the domain and range just flip-flop as well. Okay? So you can see we have a vertical asymptote along the y-axis. Okay? All right, let's try a transformation. Let's graph y equals 2 plus log base 2 of x minus 1. Okay. All right, so here we're just going to do some transformations on our log base 2 function. So recall that our parent log is this guy right here. So let's do that. So our parent function, x, y equals log base 2 of x. Just recopying that. And transform this, right? Transform. So let's look at the transformations that have been done. So here we're grouped inside with the x. So this represents a horizontal shift to the right. Right? Horizontal shift right 1. And this is a vertical shift, right? Vertical shift. In which direction? Up 2. This is positive. Up 2. Okay. So let's see what we can do with our x's and y's. So for horizontal shifting to the right 2, to the right 1, Then we're just going to add 1 to all the x's. That's the opposite of what you see there. And vertical shift up 2, we're going to add 2 to all y's. Okay? So the y's should be easy. Just add 2 to this entire column. So we'll get 0, 1, 2, 3, 4. And for our x's, we're going to add 1 to everything. So this guy will be 5, 3, 2, 1.5, 1.5, and 1 1/4, 1.25. Okay. All right, and then we just have to graph those points. So our x's range from looking like a little past 1 to 5. And our y's looks like all positive. Okay. All right, so let's graph this one. 1.25 comma 0 will be about there. 1.51. 2, 2. 3, 3. And 5, 4. So following those. Now what's it going to do back past here? Well, notice that we have horizontally shifted it to the right 1 unit, right? We shifted it to the right 1 unit. So recall from the last problem, we had our vertical asymptote of y equals 0, right? So when we shift to the right, that asymptote is going to also shift to the right. So you can see here that the asymptote would be now at x equals 1 rather than x equals 0. Okay? So our log function is just going to ride along that vertical asymptote. Okay. So again, we handle these log functions the same way we've done throughout the year with graphing. Now recall that from last lecture we had a special base, right, for our exponential. Recall the natural base e. So the natural base is e here. This gave us the natural exponential function y equals e to the x, right? And e was approximately 2.718, right? So with this natural base e, there's also, because we have an inverse here, we have the natural log function as well. So representing this as a logarithm is simple. So definition, the natural log function is y equals log base e of x, and it commonly written y equals ln of x, okay? So this is written. So instead of writing log base e, what we do is put ln there for the natural log, right? So we will see this a lot more, okay? Properties of logs. We have several properties that come out of the properties of exponentials, okay? So, We've seen this before. Log base b of 1 is always equivalent to 0. It doesn't matter what the base is because b raised to the 0 power is 1. Log base b of b is equal to what? Well, let's think. What power do I raise b to get b? That would be 1. Okay. 3. Log base b of b to the x is what? Well, remember logs as, what do I raise b to get b to the x? Well, that's simple, right? That's just x. So you can kind of think about if we take the log base b of some exponential with the base b, the log b and the exponential b kind of cancel each other out, and it just drops out the x there. Okay. Let's do some examples. Simplify. How about log base root 3 of root 3? What's that equal to? Well, using this property here, we know that what power do we raise the square root of 3 to get the square root of 3? And that would be 1. Right? About log base 6 of 1. Done that before. Anything raised to the 0 power is 1. And then last, let's try the natural log of e to the 5th power is what? Well, remember that the natural log is the same thing as like log base e of e to the 5, right? So you can think about this log e and this exponential e kind of canceling, and it just spits out the 5. Okay. There are a few other properties of logs that we can utilize. So laws of logarithms. For any base b greater than 0, b not 1, and positive numbers m and n, 1, log base b of m times n can be expressed as the sum of two logs, log base b of m plus log base b of n. Okay. All right, so where does this come from? So here is the proof. So we know that log base b of m times n let's say equals x is equivalent to the exponential statement b to the x equals m times n. Right? And log base b of m equals, let's say, y is equivalent to b to the y equals m. And log base b of n equals, let's say, z is equivalent to b to the z equals n. Right? Therefore, if we look here, this guy, using these two expressions, this is equivalent, so b to the x equals b to the y times b to the z. Right? So if b to the x equals b to the y times b to the z, then what is y? Equals b to the log base b of m times b to the log base b of n. And remember, when we multiply with like bases, this is equivalent to b to the log base b of m plus log base b of n. Which means that x must be equal to log base b of m plus log base b of m. And x originally was log base b of m times n. Okay. So, what we're doing is just utilizing this property to kind of expand this log, or we could go backwards and collapse this log. Okay. A couple more properties or laws of logarithms. It deals with division. So if we have m divided by n, that's the same thing as log base b of m minus log base b of n. So when we do a division, it turns out that we can actually do a subtraction. Okay. This also comes from a property of exponents, but I won't go through the proof there. And then last, log base b of m to the nth power equals n times log base b of m. So basically what we can do is just move this power out to the front. So let's look at a proof for this one. Why is that the case? Well, what's m to the n is just m times m times m times m n times, right? So log base b of m times m times m dot 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 n times, right? So this is m multiplied n times. Right? So what's this equivalent to? Well, if we use property number 1, right? Property number 1 was that we can express this multiplication as the sum of two logs. Well, if we have m times n times another letter, we could just add another log. That's the same thing that what we have here. So we have the log of a big old multiplication, which would be log base b of m plus log base b of m plus da 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 plus log base b of m. So this is the sum of a bunch of log base b of m's, right? How many? Well, n of them. So there are n of these being added together, so we can just multiply the one log base b by m. Okay? So that's why this is a true statement. Okay? So let's expand the following. let's say log base 2 of 5 times x. So if you want to expand this, we're going to use property number 1, which says the log base 2 of a product is the sum of the log base 2's of the factors of the product. This would be log base 2 of 5 plus log base 2 of x. Let's try this one. Log base 2 of 5x over y. Okay. So notice log base 2 of 5x over y, we can use the second property up at the top here. First, to get that division as the subtraction of 2 logs. So this would be log base 2 of 5x minus log base 2 of y. Well, we're not done now because we know that we can expand this a little bit more, right? We've just done that at the top. So this would be log base 2 of 5 plus log base 2 of x minus log base 2 of y. Let's do one more. Log base 2 of, let's say, x over y to the third power. Okay. So first we can use the third property, right? The third property says if we have something being raised to a power, we can just move that power out to the front of the log. So let's do that first. So 3 comes out, times by the log of base 2 of x over y. And we know that the log base 2 of x over y can be simplified using the second property up there. So 3 times log base 2 of x minus log base 2 of y. Let's do one more. Log base 2 of, let's do x to the 5th times y to the 4th. We'll notice that we're raising these things to 2 separate powers, so we can't really pull anything off because it's not just one power like it was before. So let's first expand it by doing the addition rule. So log base 2 of x to the 5th plus log base 2 of y to the 4th. And now, since we have log base 2 of something to a power, in each case, we can pull those powers out to the front of their logs. So 5 times log base 2 of x plus 4 times log base 2 of y. Okay. Now let's go in the reverse order. So we want to condense the following. Let's say 1/2 the natural log of 36 plus the natural log of let's say 2 times the natural log of 4 minus the natural log of 0. Oh, excuse me, of 1. Let's do 3. Natural log of 3. Okay. All right, so when we condense, we kind of want to go back through that list and take care of any multiples we see because we know we can make them powers. Then we'll take care of any multiplications and divisions separately. Okay, so let's look here. We can rewrite this by replacing the powers back inside of the natural logs here. So natural log of 36 to the 1/2 plus natural log of 4 squared. We're just moving those multiples back to the powers. And this guy doesn't have a multiple. Right. We can actually simplify this since there's some numbers. So natural log of 6 plus natural log 36 to the 1/2 is like the square root of 36, so that's 6. Natural log of 4 squared is 16 minus natural log of 3. Right. Now we can condense this one step, right? Because we know that the sum of two natural logs with like bases is equal to the natural log of the product of what's inside here. We're just using that first property, that one here, right? So we're going backwards. So we have this. That's our natural log of 6 plus natural log of 16. So we're going to go back to this property here. So that's going to give us the natural log of 6 times 16 minus the natural log of 3. And then we know that the minus follows this property, right? So we have this kind of format with our natural logs. So we can go backwards to get it to be one logarithm with the natural base and its division here. So we can write this as the natural log of 6 times 16 over 3, which can be reduced. So this is 6 times 16 over 3 is 32. So this above expression here is just a fancy way to write the natural log of 32. Let's try one more. We want to do this one here. So the natural log of x minus the natural log of y minus 2 natural log of x cubed minus 4 natural log of y. Okay. Well, if we notice here, we can actually condense this guy here first, so let's do that. This is the natural log of x over y, right? The subtraction becomes a division, and these guys become one natural log. Minus 2. We can actually put this power at the top here, so this is like natural log of x cubed squared minus 4 natural log of y. So x cubed squared, what's that? Well, this is a power to a power, so we'll multiply. So it's natural log of x over y minus natural log of x to the 6th minus 4 natural log of y. This can be condensed, so it's going to be the natural log of x over y over x to the 6th minus... Oh, we can put this power up there, natural log of y to the 4th. Now let's see how we can simplify this. So this is going to be, so notice x over y divided by x to the 6th is equal to x over y times 1 over x to the 6th. So 1x cancels here, gives us a 5. This is the natural log of 1 over y x to the 5 minus the natural log of y to the 4th. And one last condensing gives 1 over yx to the 5th divided by y to the 4th, which we can also simplify. So 1 over yx to the 5th times this reciprocal 1 over y to the 4th, which is 1 over y to the 5th x to the 5th. This is natural log of 1 over y to the 5th x to the 5th. All right, you should be able to do your assignment now.